My name's Gordon. I'm one of the docents, and there's a whole bunch of us that are docents that are working here tonight. They're scattered around either outside or some of us are inside as well. So we're the volunteers that brought the program to you tonight. I'll introduce him in a moment, who's our guest. But I also want to thank, before we go any further, our close partners, the El Dorado County Office of Education, whose Jim this is, and Kevin, who's running the AV back there today. So EDCO, as it's known, El Dorado County Office of Education, thank you very much for being our partner and for providing the venue tonight. We appreciate it. And we're very appreciative of the air conditioning. Even better. So Tim is a NASA ambassador. So if you meet him afterwards and refer to him as ambassador, not Tim. Okay. He is a NASA ambassador, and you do something like, what, 50 presentations a year to the public? Okay, 104th in 5 years, so 20 odd presentations per year. And so he's up to date on all the latest educational information that NASA has to offer. From a biography standpoint, a couple things that I noticed for Tim is he got his real jolt about wanting to know more about outer space and maybe even being an astronaut when he was 13 years old and got to see a launch. What was the launch? Vandenberg. It was a missile from Vandenberg. Not an ICBM. Right now. Good. Glad to hear that. And Tim is also associated with the Aerospace Museum, and he has been both a board member and you were the interim director for a while as well, a few years ago, right? And today he works for, is it Lux Aircraft? Lux Aircraft at McClellan. So if you need to rent a luxury aircraft to go to the Cayman Islands for your vacation home, Tim's your guy. Okay? You can find him there. Or even San Francisco. Okay, so without further ado, I'm going to turn it over to our guest speaker tonight. Please welcome Tim Pinkney.
Delighted to have you all here, and I'm glad my wife is here because she's never seen me make a presentation. It's delightful to be here. I've been a NASA ambassador for 5 years now, and Webb is the most exciting project that's come along in the 5 years that I've been here. This is the second presentation I've had since we got the photos out. I don't know if you ever heard Carl Sagan, the noted author and astronomer, say telescopes are time machines. With them we can look back to the goal has always been the Big Bang. And we know when that was, about 13.7 or 8 billion years ago. And Webb is going to get us very close to that. And I'll show you some pictures about that. But Webb is the most complex, most capable, most sophisticated, yes, and most expensive telescope that we've ever put into space. And it's expected now to be there for 20 years. Hubble's been there 32 years. I mean, some people in this room weren't even born yet, were you? No, not at all. Well, one of the things that Webb has is that it has the capability to more than just take pictures, pretty pictures. And Hubble has done a wonderful job of that. But I'll show you some Hubble pictures that were very famous. And all I can say is, you ain't seen nothing yet, because this is truly spectacular. But one of the other things that Webb is doing is helping us better understand ourselves and our place in the universe. And where did we come from? You know, we're all made out of stardust. And so where did we come from and where did that stardust come from? And then ultimately, everyone's asking the question, at least at NASA, are we alone? And just 2 weeks ago when these photos came out, I was listening to an astrophysicist from NASA that was in a public forum, and we have about 400 billion stars in the Milky Way. And every star has at least one planet. I mean, our star's got 8 planets. 9 if you count Pluto, you know? So the astrophysicist said with 800 billion planets, There is somebody on the other side of the Milky Way with a telescope that they put up in space looking to see if there's life on the other side of the Milky Way. She believes that there are intelligent life just in our own galaxy. And NASA's recent count of galaxies is now 2 trillion galaxies. These numbers become very hard to comprehend. This is a time machine that takes us back to the Big Bang, well, almost to the Big Bang. So this is what we believe the universe looks like. That the Big Bang happened here, and then for a couple 100 million years, which is just, wow. So we've got the Big Bang. Here we are at 13.7 billion years since the Big Bang, and the goal for Webb is to get within a few 100 million years. That's 98.5% of all the history since the Big Bang. That's how far back our time machine called Webb can go. So today we're going to talk about, we've already done the introduction, the electromagnetic spectrum, telescopes, the Webb telescope's goals, its images, and conclusion. So let's go into the introduction. So how many third graders do we have with us today? Not yet. You don't have. Fourth graders? Yeah, okay, fifth graders? I want to know where my future astronauts and space people are. Can't see there, okay. Sixth graders? Seventh graders? Elementary school. Anybody in elementary school? And how about high school? Okay, cool. Great. You're the one who gets all the prizes. All the adults don't get them, okay? But you have to answer the question. I got my start in, this is Mom and Dad and little Top Gun Tim, standing in the wing of our family airplane. I was about 6. Then we were off going to air shows, and that was the lead pilot, commander of the Air Force's Thunderbirds out in Bakersfield. Then Dad bought me a rocket, so I was about just getting into 8th grade high school at that age. Got interested in flying jets, and 20 years of flying jets off of aircraft carriers in Vietnam. And this is a picture. Thank you. How many of you have seen the old Top Gun? The original Top Gun? Yeah. Speed is life. Well, you'll recognize then these 2 airplanes on the right are F-14s. When I was in the fleet in Vietnam, they were brand new, and my airplane's the one in the front. We used to call it the ugly. The F-14s were called cool fighter pilots. We provided electronic warfare jamming. But that's Goose and Maverick in the back, and Ice and somebody else who were flying on my wing. Okay. How many of you have seen the new Top Gun? Good for you. Yeah. How many have seen it 2 times? How many have seen it 3 times? How many have seen it 4 times? Oh, come on. I've seen it 5 times. I have. And tomorrow, Bruce and I are going on the 6th time. And I come back, that is realistic fighter flying. You will not find a better movie. You will not find a more accurate movie. I've been there 5 times looking for something wrong. Not. It is not found. I ended up just sweating because I'm pulling cheese. These guys are. Ask my wife. I grossed her out one night. She goes, "What's all this?" I was flying those jets. Okay, so now you know, and there I am, all grown up now. So that's a little bit of my background, and I have to have the disclosure. Whatever I say is my thoughts. It's not NASA or Jet Propulsion Laboratory. The Solar System Ambassador Program is one that NASA runs, and I saw a Scoutmaster who had a solar system badge. I guess he's not here now. There's about over 1,000 of us, and we're out here to tell the public, give you some idea of what you get your money worth for NASA. And NASA's phrase, this is their job. I thought that was a pretty cool assignment. That's better than to go where no man has ever gone before. Now we're going on to something else. In order to understand what the Webb telescope is all about and why it's so special, is you need to know a little bit about the electromagnetic spectrum. How many were you able to see next door at the Boy Scouts infrared light versus normal light, visual light that we can all see? Okay, good. So here it is. You may have learned this in high school or science. How many have seen this before or know this information? Just so I have some idea. Okay, well, the class is dismissed, that's enough. For powerful stuff, we've heard of gamma rays, because we've all had guns, at least boys did, when we were kids. We've all had x-rays. Ultraviolet is how you work on your tan in one of those beds. Visible light is what you and I are seeing right now. And that's what humans, that's the range that we have. But then you go into, all starlight starts out as ultraviolet light. There's going to be a quiz on that, so just remember ultraviolet. On the other side, we have infrared, which also includes microwaves. We've all had those. Radio waves we listen to. Infrared is how you heat your food, or when you go outside and you get sun on your face and it's warm, that's actually infrared energy that your skin is feeling. So you can see infrared when you feel that warmth. So you can do two parts of electromagnetic spectrum. Here's a couple of space telescopes that we've had. Webb is where it's been most of our time. You can see it's in the infrared. Hubble is in the visible, and then Chandra, which has been working for quite some time, also is in the X-ray. And each telescope focuses on a certain band. No telescope handles all of those. This is a picture now in the lower right-hand corner. This is looking at a nebula, which is a bunch of gas and dust. And it has a black hole in it, and you'll see a jet coming out of the black hole. But we're going to be looking at the same thing, same object, in radio and 4 other visual, so you can see how it changes. So there we go with radio. Going to mutate to infrared. Same object. Very cool, isn't it? And when you put them all together, see the jet coming out of there, the black hole. That's an X-ray. You put it all together, look at how beautiful that is. Yeah. So those are your hard-earned taxpayer dollars at work. When you can say ooh and ah about the money you send the IRS. Okay, so now we're going to focus more on infrared. To use this, to talk about this, I use mercouts, which are warm-blooded varmints of some sort, and a cold water crocodile. So that's the way it looks. But when you look in the infrared, you see the mercats are bright because they're warm, whereas the crocodile is kind of dull because it's cold-blooded. Let me back up there for a second. So that's the way we're going to be looking at things with James Webb in the infrared. Here's visible light. There's 2 wavelengths of infrared that Webb uses, the near infrared and the mid infrared. There's also a far infrared, but we don't have that capability. But what happens with You see the guy there with his black plastic bag. In infrared, you can see through the black trash bag. Space is full of dust and junk. That was a very technical term. Space and gas and dust. The clouds pictures. And so here, infrared, you can see just how easy you can see through that. And that's why all the criteria that was required for Webb all had to do so you can see things in infrared. And I've already told you that you can see, feel infrared on your skin. So here's a classic picture, Pillars of Creation. That's a very highly desirable collection of solar system planets and information. So this is cool stuff if you're an adult. For kids, this is really cool. I want you to get one for sure. So on the left, looking up from where kind of the brown shoulder is up to the very top of that first pillar. Want to guess how big that is? Do I hear 1 trillion miles? Do I hear 2 trillion miles? How many do you think? If you round up to 5, it's actually 24 trillion miles. The bottom of it, just that first shoulder before the second one, is 30 trillion miles. And on a picture, if I showed the whole thing, the whole picture is this big, and these things are this big. So it's quadrillions of miles. And here's what happens when you get something like Webb. Walk away from my chin. Where's my assistant? Banana. Here, Banana. We're going to just look. All right, so here's what Webb's going to show us. So what you're seeing on the left in the blue background, that's gas and dust being photographed. And dust is everywhere in the solar system, and dust around our star created Earth and all the other 3 rocky planets. Look at the background, you can see all those stars, and then you can almost see through each of the pillars. It gets rid of that dust. So that's the whole reason we built Webb on infrared. Excuse me. I like this picture. There's been lots of artists' renderings of, we're going to be looking back 13 years, and I think this is the best picture I like for Webb. And I'm going to show you. Okay. We're going to, once again, I just want to drive home the point. How's my time doing? Okay. On the topic is red shifting of light. Light changing from blue to red because the space around us is expanding. And so, how many are familiar with the Doppler effect of trains or ambulances? Okay, it's basically a Doppler effect. So over here on the right we have, remember, the powerful ultraviolet coming out first from all the galaxies. And before I jump over to Webb, I'm going to show you that we're going to be here about 90 minutes, and you've probably been here longer than that. But in that time, our universe has expanded over 235,000 miles while you're sitting here. So the moon is just 5,000 miles more. So it's amazing that we've already, the universe in all directions has expanded. That also means 10 million miles a day, 300 million miles a month, 3.6 billion miles a year, the universe is expanding. And for the 20-year life expectancy of Webb, we're looking at 72 billion, if my math is correct. So watch over here, what starts out as powerful ultraviolet. Over time, redshifts. And so it's redshifted into the infrared. And I have a very technical visual aid here, a moment. I went to my medicine cabinet for this technical aid, but this is basically just a way coming out of the ultraviolet in this very uniform shape. But as time goes by, it stretches. And you see, as it stretches, it becomes, I can't make it turn to red, but it's red. This part stays steady, as I can do that. And as it stretches out, it changes. So all the pictures you see coming from Webb have gone through it basically is technically only can see this stretch, this red shift, the infrared part. Do I need to say that again? I see a lot of frowns. Well, thank you. All right, I'll put my expensive training. We spent a lot of money, over $10 billion building this over the last 25 years. Webb has a design, but it took 9 years to design it and then redesign it, because as science learned more, they kept saying, well, to answer that question, we need to have this. So it just kept going and going. It took 10, 11 years to build. And what's Webb been doing for the last 5 years? Be tested and tested and tested and tested. Because we all know that Hubble orbits the Earth, and we sent up 5 repairs for Hubble. Webb is 1 million miles out. So it goes past the moon, it's 250,000, goes 3 times farther, and it's out there all by itself for 1 million miles. We can't fix it. We can't get to it. One-time shot. $10 billion, 20 years in the making. We got perfection. We really did. NASA really did well. It was a little underestimated for the budget. But you know, that's government for you, right? Or contractors for you. And as I mentioned before, the European Space Agency's Ariane 5 rocket put Webb exactly where it was supposed to be. I mean, exactly. And gave us 10 years more fuel to enjoy the benefits of Webb. So it took off on Christmas morning. Got about 75 miles high, less than 3.5 minutes later, got rid of its shroud. And the whole idea of this Webb would barely fit in this room. 46 feet wide, 76 feet long, and it's got to fit in a capsule that's 15 feet big. That was a technological marvel. A lot of brainiacs. And then when it got up high enough, on the left, you can see that gold ring, which just said, "You're out of here." And Webb was on its way to a point called L2, Lagrange point 2. And if you saw the Boy Scout, they had a graph on that. I had one too, but I took it out to save time. But know that while Hubble orbits the Earth, Webb orbits the sun, just like we orbit the sun. So Webb is always out here, and we're orbiting the sun. And Webb can see at any one time for about 80 degrees in that whole area. And so you can tilt down a little bit, see lower, tilt up high, but it sees a lot. And since there are 2 trillion galaxies, it's got a lot to photograph and learn about. Webb has 2 sides and one little fly you can see up there at the top. There's the hot side and there's the cold side. When we're dealing with the infrared, we want to be as cold as possible because we're trying to find heat, because heat is infrared. Okay, that sound good? You got it? Got it, okay. So the hot side is 185 degrees Fahrenheit, and the cold side had to be minus 385. So in 6 feet, where am I go here? Yeah. In 6 feet, it goes from those two temperatures, 600 degrees in 6 feet. And space is minus 385 degrees Fahrenheit, give or take a few degrees. But that is not even cold enough for one of the instruments. Webb has its own refrigerator on board to bring down one of the instruments even just barely above above absolute zero, which is measured in Kelvin. So we got Fahrenheit, centigrade, and Kelvin, which is what scientists use. So the one instrument has to be at 6 degrees Kelvin, which is remarkably cold. This is saran wrap, basically like saran wrap. It's as thick as saran wrap. The top layer, the bottom layer, the heat layer, about 13, is two saran wrap thick. The rest of them are one saran wrap thick. And if you may have heard that Webb got kicked with a stone, basically, and it's got a little hole in it now, and engineers planned for that. So I'll talk about that in a second. But you can also see up here that square. Every 6 feet is a panel, double stowed, so that if a meteor goes through that one panel, it won't rip the entire, basically, tennis court size shape. Yeah, biggest, literally, fitting inside here, and 3 stories high, so we're going to go 30 feet up. I mean, that's how big Webb is. And it needs that sun shield in order to not get baked and ruin all the instruments that are so sensitive to heat. And if you're interested in sun protection, wear 6 layers of this saran wrap and you'll never get a tan. So you've seen some of the people wearing that pin of the octagon there on the here. These are beryllium-backed. Beryllium weighs is a very stable metal that does not contract in deep space, in deep cold, minus 380 something, with a layer of 24 karat gold. And at 24 karat gold, that's 270 square feet. So 10 feet by 27 feet, 270 square feet of mirror. The size of a marble. That is how much gold is on all of those, all 18 of those mirrors. And it's about the weight of a golf ball, but it's the size of a marble, spread out at 3 microns thick. But gold is used because it is the most effective metal to absorb infrared light. So there's a reason for everything, but it's also marvelous technique. So there it is. And we've never had a folding telescope. So these 3 here and those 3 there folded back inside themselves to fit inside the entire rocket. That had never been done. And then we had to, then it was open. There were 314 single fail-safe items. They didn't work. Webb didn't work. And so it was a lot of, took 2 weeks to unfold everything. And there was a lot of, when people land on Mars, or the rovers do, there's 7 minutes of hell, 7 minutes of terror. This had 2 weeks of it. So here are the mirrors, 18 of the hexagons. And they're hexagons so they can fit in together and fold easily. And they are aligned in such a way that they are the alignment is 0.0002 aligning with each other. They had to align perfectly, otherwise it wouldn't be a good mirror, and we wouldn't have great images. So we were the main lead. The European Space Agency was involved heavily with the rocket and also building one of the instruments, and the Canadians also helped us. So this is my equal opportunity for flying for all three space agencies. Here's the hexagons, and this happened about 2 weeks ago, actually it was in May, that a spacewalk came and hit right there, and it is incorruptible. They've adjusted it as much as they can, they be NASA, and it's not perfect. But even with the ding in the glass, the performance of Webb is beyond calibration expectation. Again, we got our money's worth, and it broke, and it's even better than they ever expected it to be after even breaking. And it's not close, it's just got a hole in it, you know? Our question is, what's the likelihood of that happening again? It was designed, Webb was designed knowing it would get hit, because there's just all sorts of space rocks out there, and there's been one hit every month on an average, but the hits are as big as a grain of sand in 5 out of the 6 cases. The likelihood this will happen again in 20 years, pretty high. I think 20 years from now, you come back, we're going to look at kind of an old, decrepit, broken mirror that's still getting by. You know, it's like Hubble at 32 years, it still gets a good image, but it's got aches and pains and hard turning, its joints are hurt. So we think this is going to be a telescope, you know, for all the kids in here. It'll be your whole childhood and young adult life. Pretty cool. Here's when lights come in. Can you see the yellow there? Light from stars. It then goes to the secondary mirror, which is what those arms are holding that out. And this is the way all telescopes work. And then it goes down the hole, there we go, into, there's 4 instruments that the light goes into at that point. And it's amazing how it bounces around for the different instruments. And I thought, you really want to see the pictures, you don't want to know how to build the watch. So I am not talking about specifically all the instruments in there, but I'll talk about the capabilities. There are 3 that are in the near infrared, NIR, and 1 in the mid infrared. So these each have their own specialty, and this picture is full. Another picture will show you that. That's a Hubble picture, just pretty picture to get you psyched up for what Webb is going to do. When I was introduced, when I make presentations here, I promote, or at least make you all aware of the Aerospace Museum of California down at McClellan off of Interstate 80. And when I'm down there giving presentations, I talk about this place so that we have reciprocity. And so, the community service announcement is, how many people have been to the Aerospace Museum of California? Okay, well, that gives a lot of you an opportunity for seeing that because it's really impressive. If you like military aircraft, there's over 35 of them. There's a great section of space in there. And anybody see Tom Cruise movie Oblivion? Did anybody see it? A couple people? Well, that's the actual prop. That is, Tom Cruise sat in that seat, and that cost $8 million for a prop. And it was sitting in a studio back lot. We said, hey, can we have it? And they said, we'll only loan it. And he said, okay, indefinite loan it to us. Indefinite. So, Google had an offshoot of trying to generate electricity out of a kite that flew in circles. And it had a rope or string holding it, and those propellers generated enough electricity to light up 300 homes. And the idea was for each development to kind of be self-sufficient with their kite that just went around and around in circles. That's hanging off the roof of the Aerospace Museum. Okay, so this is for our students in the audience. See how well our audience, our adults, know whether or not the solar system. How many named moons do we have in the solar system? Anybody any student want to guess? Yes, sir. That's a good guess. He guessed D, delta, but that's not correct. Let me ask you again. Yes. Give me a letter. C is that we have a winner, and where's my assistant here? So, how many of you knew the formal name of our moon, Luna? How many knew that? Okay. Because we call it a moon, but there's over 200 other moons that have names on them already in the solar system. So, 200 is the correct answer. Think about that question. Of that 200, how many have liquid water under ice exteriors? Let me see if I got somebody else first. Do I have a student somewhere that ventures? Yes. Well, I need to give you the choice here. Wait a second. That would have been very good if you got the answer. So there's the choices. Now you want to try again? Oh, he's right. How many of you knew that there were 12 planets, 12, what are those called? Moons, that had liquid water in our own solar system? We're going to be going, we've got NASA has a space flight already planned for Europa, they're in the top line. Up to 200 moons, how many moons have an atmosphere? Our moon doesn't have an atmosphere. There's only one that has an atmosphere and has liquid on top of it, on the surface, and that's Titan. And we're sending a mission called Dragonfly to Titan. We'll have in 3 years, we'll talk about that. Picture there of our president. How many of you have been to Mount Rushmore? Okay, how many of you have been to the backside of Mount Rushmore? Well, I'm glad you're here tonight because we've discovered 4 more moons. I'm glad you laughed at that one. I also have one in a different crowd. I have one for equal opportunity and the women's posterior show, but I thought this would be safer. Again, my disclaimer. Just to remind you all what it is. So let's talk about our spacecraft here. We're going to get into that. The mission is to look back farther in time than any other telescope has done that before. And the goals are 4. This is not a goal, this is a big picture. But we want to go back to the Big Bang. What is it that we can find out? So we're going to look for galaxies just after the Big Bang. First came stars, then came galaxies. We don't know how that all happened. We don't know how galaxies went from little galaxies to big galaxies. We think we know how stars form, but not sure exactly how planetary systems form. So we have our sun, we've got 8 planets. How'd that all exactly happen? And then let's learn some more about our own solar system. We got the most powerful telescope in the world, in the universe right now, as far as we know. So goal number 1 is to look at the big picture after the Big Bang. And so what we have here is the Big Bang, and then the universe in microseconds expanded. And then as this mass expanded for 400,000 years, it was dark ages, so there was only hydrogen, which has one atom and one electron. But somehow that gravity started pulling them together and we started getting helium. And then the helium and the hydrogen got together and started stars. And pretty soon the stars burned off all the old gas. And we had, from the dark ages where there was no electrons circling around, to all of a sudden the first star about 400 million years. And since then, we've got another 13 plus billion years that we've expanded out. We don't know much about that other than the big picture we just showed. So, what were the galaxies like? Or the first stars like? We really don't know. But I like that first picture of gas circling around and gravity pulling it all together. And once the stars start, then how do you get a galaxy pulling that together? Well, we know it's gravity, we think it's gravity, but we're not quite sure how that all comes to be. Here are galaxies that are colliding. Their gravitational force has pulled each of them closer and closer. And how many of you have heard of the Andromeda galaxy, at least in movies or something else? We're going to collide with that. Our Milky Way is going to merge with Andromeda, just like the upper left-hand corner, or maybe the upper right-hand corner. But that's somewhere between 14 and 20 billion years from now. Don't skip school because you think the galaxies are going to merge. So here's one of the guesses that we just had baby galaxies that became medium galaxies that moved into, there we go. And so they combine, just like we saw those pictures. That's what we think happened. And then we have something like the Milky Way. The first, very bottom are much more irregular shaped. They're not more spiral. And so we're trying to learn exactly how that all happens. And Webb is going to give us some wonderful pictures. This is a picture done by Hubble of an actual star in the center, which is the yellow inside the first ring. That's a star getting close together. And in those dark rings are where dust is collecting and the gas is coalescing and getting all together. And eventually that will be a star and an entire planetary system, a solar system. And Webb has already picked out 17. These are all from Hubble, but the pictures here just to show you from kind of an immature to a getting more mature. And then you can see very clear delineation there. And so the dust has been cleared out, and we're getting rings, and those rings will eventually become planets. And then lastly, this is a question for the youth. We're going to learn some more about our own solar system. So what child, youth, kid, student can tell me what the white is there? Well, you know everything. I got a guy back here, but let me. So the answer to what the white up there is?
Chemical.
They're actually chunks of rock, icy rock. But there wasn't quite the full answer. Well, you're not a kid. Wait a second, let's see if there's any kids over here. How about, oh, this one in the back here. Those are the rings of Saturn. And that white spot is one of the moons of Saturn. And the yellow, we've already talked about. Who remembers what's the name of the only moon that has an atmosphere? A yellow, hazy atmosphere.
Titan.
Titan is the answer. Man, we've got some good ones here. Okay. Well, here's something that Webb took. This is Jupiter. Jupiter is pretty hot, and it's relatively close. It's 450 billion years. How many of you took the walk out there from the early solar system to out there Jupiter being? In 1 second, 1 minute. Look at this. Look at this. This is the ring around Jupiter, just like Saturn does. And Neptune and Uranus also have rings around them. We can't see them by visible because they're so dark, but they have heat even that far out. And so we're going to see a lot more about our own solar system. And that Jupiter image doesn't look very much like Jupiter, but you can see the really hot spots at the top and the bottom, as well as the stripes, just like you see in color pictures. So who was James Webb? He was the second administrator of NASA. And what was significant, just shortly after John Glenn did his orbital flight in 1962, he said, we need to see further out into the universe. And 60 years ago this year, he predicted we needed to have a telescope. And so for the last 20 years, we've called the telescope that was being built the Webb telescope. That's how the name came to be. Now you know Mr. Webb. That's also the only time a satellite has been named for a administrator rather than a scientist. Hubble is a scientist, and many other, Spitzer, etc. And just to point out that Hubble is supposed to live for another 10 years, providing good information to us, and that's so. Webb is not a replacement for Hubble, it's just a different, one's in visual, one's in infrared. And this is a little bit of just comparison so you know that Hubble is the size of a bus. I've been describing, look at that, it's 70 feet long and 46 feet wide. Big. And to give you a perspective, there's some of the people down in, where that was. Anyway, 40 million hours to put Webb together from design through the whole thing. And here's the significance. The size of your mirror gives you better clarity and greater distance. And so Hubble is at that point 2.5 meters wide. JWST, James Webb Space Telescope, is 7 times bigger, and the electronics are so much superior to Hubble that overall we get 100 times better information from Webb than we did from Hubble. These are the capabilities, and more than show you those pictures to go through them until tight on time, that I'm going to show you my favorite and amazing technology called the near infrared spectrometer. It actually is 4 postage size, kind of big size postage, of lenses, not lenses, shutters. So your camera has 1 shutter, your iPhone might have 2 shutters, Hubble only has 1 shutter. This has 250,000 shutters. And look how tiny. And you can open 100 of them at once. So let me show you how that works. There you see a close-up, and you're actually looking at the shutters being open to take pictures. And to better visualize that, we're getting closer and then closer again. And these are all run by magnet, by electricity. Switch on, switch off. It's locked, it's open. But it's amazing that you've got 250,000 circuits to go there. Here's what it looks like. You see that star at the top that you want in the black, and then you can see it down there at the bottom, so you open up that shutter. But you don't want to have all 2 million objects there, so then you open up that shutter, and you open up that shutter. Say, oh, okay. And the other pictures are there. I didn't want to go through that whole group with you. And then Webb looks a different way, it goes around the Earth a little bit more, around the sun, and we get the same thing. So this will give us a chance to have 100 pictures at one time, where Hubble only takes one at a time. So the amount of information, and it downloads 65 gigabytes every 24 hours, which is a fast speed, which is a billion miles away. So here's what you waited for. Yes, thank you very much for your attention and listening to that, but I wanted to give you that background so you have a greater appreciation of what we're going to look at. First was a image. All of Webb's pictures of stars that are close are 8-sided like this. And the reason it comes that way is because the strut, the actual 3 struts that hold up the secondary mirror, actually block sunlight coming through or any light. And they end up giving a 6-point more horizontal. The mirror, the hexagons, each do a star like this. And the bright people at NASA said, well, why don't we get the struts to make sure that they match here and there and there, and we'll just have those little 2 squirts. So every star, you see there's the 1, 2, 3, 4, 3, 4, 5, 6, little squirt, little squirt. So all the close pictures will be, of all the close stars, will look like that. So you'll be able to tell right off the bat whether it's close or far. Already in its second week, Webb found something that we think goes back, it hasn't been confirmed yet, but it's believed to be 100 million years older than anything Hubble's ever done, and it is within 300,000 years of the Big Bang. Our goal is 200,000, so we're getting there just on the first week, first images. And here's a galaxy that doesn't look at all like our galaxy, but early galaxies were different. We just don't know exactly how different they are. So, in that, another goal, (7,600 light years away), and remember, light travels 6 trillion miles, so multiply 6 trillion times 760,000, and you've got how far away that is. Anybody in math major that knows that? I actually have a young lady, probably 10-year-old, figure something like that out. So, isn't that cool? Now this is actually a Hubble picture, but I wanted to give you the entire nebula, and the one we're going to be looking at is called 3324, and I'm going to blow that up. So now we're kind of looking just at that swimming pool, the blue, and show you there. Now I'm going to rotate it 90 degrees so it's looking like we normally see it. And so this is a picture of Hubble that Hubble took. And this is a close-up of that. And this was the best picture we had had since Hubble was around for the last 32 years. Best picture, most definition. The blue again is gas and dirt and dust. But when you come into Webb, I'll stop talking and just let you watch it. One thing, the entire floor, I turned. So here's this is side-by-side comparison using visual light at the top and infrared. But it gets rid of a lot of that blue gas at the top. But the inside, I mean, these are big caves that have been blown out by stars. I'll show you that a little bit better here. But when you combine both the infrared and the near infrared, you get to see a totally different collection and better perspective of what's going on in here. So I will show you that. Now those blue arrows, I'm going to back up here for a second. And can you see kind of the pinkish lines coming off? That's radiation coming from the stars glowing and bursting. And so that is constant radiation coming off those stars going up into space. And it's ionized, which means it's lost an atom, so it kind of glows. And that's because of the ultraviolet, as I said. So this is just something that we have not seen in that kind of detail. I've gotten even closer here, and to show you some things, here are the cavities and bubbles of being blown apart as these new stars just explode because they finally become combustible, become with fission. Over here in the lower left-hand corner, looks like a comet, but it's actually there's a star right there, and it's exploding gases. And if you look, the gas goes around there, and there. And that's something that we haven't seen before. So we're seeing the birth of a new star. The star is in this stage somewhere between 50,000 and 100,000 years, which is like seconds, like minutes in cosmological time. So we've never seen a picture of a star being created and getting its first, not its first steps, its first breath, literally, in the universe. And then here are developed solar systems, like the pictures I showed you, where we had 17 of them. And if you look up close here, I'll show you what that looks like. So those red dots and pink dots are all solar systems that have started. We've never seen that before. So this is just one image. We got our money's worth. I mean, it was just amazing, and it's the first week. So let me just have you look at that again with a greater appreciation of all that's going on cosmologically. And I'm curious about this cookie guy here. But there are already research papers being done on this. It's 2 weeks old, and it's soon to be published because everyone wants to say, me first, me first. I found, I discovered, I invented, whatever that was. So now we're going to look at a nebula. A nebula is a star that explodes. This one's only 2,000 light years away. And this is the best image that Hubble could get. And we were delighted with it because we never had that great of detail. The colorings are that in this particular one, blue is the hottest of all the gases. And as if we're looking essentially in like a tube, straight down. And this is the next layer coming out, and then the yellow layer comes out, and then the red layer comes out. So it's kind of just exploding, and that's what it is. So when you put Webb on that, isn't that amazing? I mean, you can see the dust rings. So again, blue, and you see the star, and so this is really hot, and it's very steep. I mean, each of these is when the star, for lack of a better word, it bursts. Okay. So it just explodes, and it takes, maybe 1,000 years to do that. And it doesn't do it evenly, so that's why it's not a perfect circle. There's a spot here, kind of bulge there. But here's 1 ring, 2 rings, 3 rings, 4 rings, 5 rings. So this is the coldest. This is the hottest. But this is on the near infrared. The special cooled down one had to be better. That's the mid infrared. And you will see, look at that change. And what's the surprise in the middle of all that? Not 1 star, but 2. We had no idea until a week ago that there were 2 stars in there. No one had ever seen them. So here's Webb from the same structures going on, essentially. You've got the hot gases here, and they kind of burp out there big time, and another burp there, another burp there, and then out here, then you can see a far one over there. So this was 12-hour exposure, I think. It can be out there for days, and imagine the detail we're going to get. So here's the comparison, so there's the 1 star, there's the 2 stars, the prize. And this is just helping you visualize that the gas is going to the left and right that way, and then this one, the teal color is colder going up more vertical. So that's, we just did not know that kind of detail before. And then closer up here, I've blown up the 2 stars. The red star is a dead star. It has exploded. It caused most of the gas around. But it should not be cloaked in dust. It should be kind of burned off. We don't know why it isn't. The white dwarf still has diffraction spikes. Remember the 6 spikes that you normally see. And the white dwarf shouldn't have those at this stage of its life because it's basically burned up all of its fuel and it's shrinking. I'm shrinking, okay. So, we don't know that. We're going to find out. Stay tuned. Next time we have an update, we may know the answer to that. So, a few white dwarf stars. They were giant stars like the size of our sun, and they got dwarfed. Basically blew off all their energy. 1 teaspoon, the weight of an elephant. Kind of hard to figure out what 6 trillion is, or let alone a spoonful to be as heavy as an elephant. And if you're around long enough, you'll see that 97% of all stars in our solar system will eventually be a white dwarf. But you got to be around for a couple more billion of years. I mean, I think for in your dying days to have 100 billion more years of life is a pretty good life. And eventually they become black dwarfs, which I'd never heard of before, but pretty remarkable. So here's a interesting, we found this little blob over on the right-hand side, left-hand side, and what that might be. I know you're going to guess, but let me see if there's somebody over here. Is there a student who might know what the answer is, or what that white blob is? We have a young man here who said it's a galaxy, and guess what? It's not an alien spaceship, it is a galaxy. So well done, good job. At first, NASA thought that those were actually rays coming from the nebula, scooting through a little bit of a hole here in the gas, but somehow they figured out that was an edge on for a galaxy. Okay, so exoplanets. How many have heard of exoplanets? There was a discussion out there. So an exoplanet is any planet around any star that's not in our solar system. We have, our sun has a name, everything else is called a star. So if you have planets around it, and they all do, there are gas giants like Jupiter. There were 1,500 of them already measured. We never have had a picture of any exoplanet because the star is this big and the exoplanet is this big. So it's too bright. It's like looking at a, what's that called? When you're in the ocean and the lighthouse. There we go. The lighthouse. You can't tell that this is a lighthouse? You guys are falling asleep. You gotta wake up. Okay. The kids probably do that. It's like looking at a bumblebee or a firefly next to a lighthouse. You just can't see it because the lighthouse is too much. By the way, Webb is so powerful that it can see the heat of a bumblebee from Earth if the bumblebee was on the moon's surface. That's how sensitive the heat is. Yeah, just remarkable. Okay, so we can't get a picture of an exoplanet. This exoplanet is only, well, it's 6 quadrillion light years, miles away, but it's 1,350 degrees. Mercury, our own Mercury, first planet, it has a temperature of, I don't know how you measure it, but in the 500 degrees. This has 3 times that almost. It only takes 3.5 days to orbit. I mean, we take 365 days. This takes 3 days. So it's very, very close to the sun. Mercury has no water. No way that this exoplanet should have any moisture whatsoever. And NASA and all scientists have said, we got water at that many different ions and temperatures. So, and there are 5,000 exoplanets. So we have a lot to learn. And we're very unexpected. And here you can see in the red bracket, that's a very gentle slope. That tells the scientists that that's actually haze, not pure water vapor. There's dirt, dust, LA smog in it, I don't know, but it's got stuff in it that it shouldn't have from what our expectations would have been. And this is how we figure out light. So you got a planet over there on the left-hand side, and it goes in front of this, and the light dims down. So Webb is looking at it right down bullseye, and then when this goes across, it only lowers the light by 1.5%, very, very low, very, very little change. But Webb can measure that, and therefore it gets the reading. And this is just the first 5,000. 5,000 exoplanets. Thank you for. I need more water. How many of you seen Jimmy Stewart's? It's a wonderful life. It starts out and there are galaxies talking to each other. Well, those galaxies are known as Stephan's quintet. And in infrared, they look like that. And in mid-infrared, they look like that. So it's really a quartet plus 1, because the lower blue one is a younger one. It's got the blue stars, and it's 40 light years away. But we can't tell depth perception that far, so the other ones are 290, almost 5 times, 6 times more, 7 times more. They're side by side, just amazing. And then something that Webb has that Hubble does not have, and that is spectroscopy. How many know what spectroscopy is? How many can pronounce it? Basically, light comes in from here, from any source, any star. It's filtered, not filtered, but blocked. It goes into a grating, it goes up here, just like a light beam goes through a triangle and you get a rainbow effect through a crystal. In the crystal, or the rainbow there, every atom, every molecule has its own spectrum. Oxygen is different than carbon dioxide, it's different than hydrogen, which is different from helium, which is different from argon, etc. And so we can tell what's actually happening in here. So the red will tell us it's a dusty, star-forming region, it's far away. Blue, you're closer without dust. Light blue is significant amounts of hydrocarbons. And you get up into the green and yellow, you're talking about farther away, and also rich in hydrocarbons. So we couldn't tell this with Hubble. It's Webb that told us this information. And here's the coolest part of all of Webb. This is that same picture, but they've looked into the black hole that they knew was there, but they hadn't seen it. Atomic hydrogen iron ions atomic hydrogen at a different wavelength because it has different ionization, and molecular hydrogen. The difference between molecular hydrogen and atomic hydrogen. Molecular hydrogen is what you and I know as H in the periodic table. But atomic hydrogen is the combination of two hydrogens, and it's a different spectrum. So the cool thing that surprised everybody, the red box. How many have seen pictures of the two black holes that have been discovered in the universe and actually had photographs? A couple people? Yep, okay. Of course I expect astronomers to know that. So there it is, close up. And look what you see here. That is a black hole. It's the third time we've ever photographed a black hole. And, you know, we all know that light can't escape a black hole, but we can see all the junk going into it. And so that's what the red all around the black hole is. And in this one galaxy, this black hole, 24 million times the weight of the sun. Let that thing in for a second. 24 million times the weight of the sun. That's pretty heavy. Yeah, the answer is heavy, man. Okay. But it fires off enough light equal to 40 billion suns. So Hubble in its first week gets to discover a black hole that's a monster. And we get to see a picture of it, which is got our money's worth, folks. We took red spectroscopy near the black hole, which is at the top here. Now the outflow is junk coming out of it. Stuff goes in, stuff comes out. Ionized gas again. And there's neon. It's at the different points because of the different ionization. And we've got sulfur coming out of there at the same place. But while we're down here at the supermassive black hole, we learned that it's got colder gas. And the colder gas is basically molecular hydrogen and silicate dust. That dust is eventually going to go back out in the universe, and a couple billion years from now probably start to be a planet or be more blue stuff in the photos that we take down the road. I thought this was interesting. It sucks in gas, but it also blows out gas 450 miles per hour toward the black hole. Neon is even, and then on outgoing molecular hydrogen, 450 away. So this is just suck in, blow out. I mean, this is a remarkable amount of energy, and we've never seen this before. And this is, Hubble became famous in the first deep field. You know the story that you take a piece of grain, a grain of sand, and you hold it at arm's length at the totally black part of the universe, and then you took Hubble for 280 hours, and this is the picture they got. And scientists thought it was a waste of 11 days pointing Hubble in one direction where we knew, absolutely knew, there was no star. A grain of sand, and you get that. There's 10,000 galaxies in there. So again, back to the 2 trillion galaxies that we have. There's a galaxy showing. So here's Webb. It only took 12 hours as compared to, because you got the bigger lens and you can collect more light. There's some interesting aberrations here. There's just, again, some normal satellites. You saw that. Well, I wondered if you'd be sharp enough to catch that, because Mark Hamill, he tweeted that shortly thereafter the photo came out. I thought, I got to put that in. I just saw that last night. So, pretty cool. You saw it here first, probably. Okay, so, moving on. There we go. something that we know about, but when you have a large galaxy, a group of galaxies right here, a lot of weight, and it literally bends space and time. And these pictures right here, this and this, are the same galaxy that are on the other side of all of those big heavy billows. If you take a wine glass or any kind of glass and hold it over a candle, the candle goes like this, and then you put the glass here, and the candle becomes round, and then you come back. And so that's gravitational lensing, and so that's why that glass. This is the end of my presentation because my wine glass is empty. But 9.3 billion years ago, behind those yellow circle galaxies, is those two. That's the same galaxy, and we proved it using spectrum from the Webb. You can see there on the right-hand side, they are identical. So we knew that's the same thing. One picture with spectroscopy, you can see oxygen and hydrogen atoms going from here with only 11 billion years, and then 12 billion goes over, 13 billion goes further, and 13.1 goes even further away. So that's farther than Hubble has ever seen in just the first picture. So again, we got our money's worth on that one. But when you take the red 13.1 billion and that little red blob that you actually can't see in that picture, we get spectrum out of it, and we find that it's got hydrogen, neon, oxygen, more hydrogen, and we didn't know that from that little spot. But you see, it's also got the very early gases. It doesn't have sophisticated gas. We got oxygen, which is very common. Hydrogen, that's the second. Neon is right there in the first top 10. So we're seeing the early galaxies give us the original elements that created you and me. No one can predict what Hubble's going to find. Maybe we can find life somewhere in the universe. We hope so. I mean, that's been NASA's goal for a long, long time. And I started the evening with a quote about Carl Sagan saying the telescope is basically a time machine. I'd like to close with comments from Carl Sagan also. We are all along for the ride. Every human who's ever wondered at the majesty of the universe, every person who feels grateful that from dust and gravity and unseen matter, everything good and beautiful and true in the world was somehow made of the stuff of stars. The Webb time machine is going to give us some answers to questions we would not have ever dreamed about. And new, exciting, and literally unfathomable findings are going to continue to blow our minds. Blow our minds, it'll rewrite textbooks, and it'll help us rethink about our place in the cosmos. For your kids, this is my hope that you're at this stage of your life now, and you'll be inspired, not necessarily all to be an astronaut, but to get into astrophysics, geology, geometry, math, all of the science, technology, engineering, and math opportunities to learn high science. Remember, this is NASA's goal. We've got to be equal opportunity, so we've got boys in there too. They're in space also, for the benefit of all. That's our goal. So, what's your goal, kids, and all of us as adults, to learn more about our own galaxy and our own cosmos? And do you want to be an explorer? Do you want to go to a certain planet? Do you want to look cool in a flight suit or a spacesuit? It's whatever you want. But in less than a year, is what I said before I put this presentation together, in reality, in 2 weeks after Hubble, or 2 weeks after Webb, we're already saying, we used to believe this, but now we have. So it literally is happening right before your eyes. And from this moment forward, our lives will never be the same. Thank you, and thank you for